from last year, so we'll record it. So the two properties we are reviewing today for radicals are the product property of radicals, and then we'll review the quotient property. But the product property just says, and we've used this already, that if you have the nth root of a product, you can split that into the nth root of each individual factor, or vice versa. If you had two nth roots being multiplied together, as long as their index was the same, then you can write it as one radical. So I actually showed that in 6.4 because I was breaking apart the radicals, and I'll do that again today. But it says here, in order for a radical to be in simplest form, the radicand must contain no factors that are nth powers of an integer or polynomial. So you have to look at each individual factor and make sure that it is fully simplified within that root. So if we look at example 1a, we have the square root of 12c to the 6th d to the 3rd. So just like I showed in 6.4, I'm going to split this into square root 12 times square root of c to the 6th times the square root of d cubed. Because like I said, in 6.4, we had perfect squares, perfect cubes, and so on. Here we may not. So for example, 12 is not a perfect square, but is there a perfect square that goes into 12? 4 does. So I can split this into the square root of 4 times the square root of 3. And then I can actually take the square root of 4, which is 2. So I would have 2 square root 3 for the 12. Okay, and I like to work through these piece by piece, so simplify the square root of 12, then the square root of c to the 6th, and so on. So then if I move on to the square root of c to the 6th, now remember with exponents, you divide the exponent by the index, which for a square root is 2. I can divide 6 by 2, it's 3, so that would just be c to the 3rd power. You do have to question, though, with your variables and exponents if you need absolute value bars. So do we need absolute value bars for this? Yes, we have the even, odd. So just around the c cubed, you need absolute value bars. Then we get to the d, and I cannot divide 3 by 2 evenly. So when this happens, you still want to divide the exponent by the index. So I'm still taking 3 divided by 2. And what you're looking for then is how many times does 2 go into 3 and what's the remainder. So I know 2 goes into 3 one time and there's a remainder of 1. So these two ones, what that means is I'm going to have a d to the 1st power that will no longer be in a square root because 2 goes into 3 once. But then this remainder of 1 is going to be the exponent on the d that's still in a square root. So I still have a square root of d to the 1st because that 1 can't be divided by 2. So you should make sure in your final answer, all of your exponents should be smaller than the index. If any of your exponents are bigger than the index, it means you can still simplify it. And then do I need, for this d that's not in a square root, do I need absolute value bars? I couldn't tell if that was a yes or no. So I have an even root, but an odd power. So I don't need them here, even though this is odd. So this is your answer, but I'm going to rewrite it with the 2 square roots together in 1 square root at the end. So I would have 2 absolute value of c cubed d, and then the square root of 3d. Okay, so applying what we did in 6.4, but again, it's not going to work out as nicely as it did in 6.4. So let's look at another one. If we look at b, this is a cube root. So make sure when you are splitting apart the roots that you are including the cube, the index. So I have the cube root of 27, the cube root of y to the 12th, and the cube root of z to the 7th. So cube root of 27 That is a perfect cube, so that is 3. If it wasn't, I would be looking for perfect cubes that go into 27. So not perfect squares that go into it, but perfect cubes. Then I have cube root of y to the 12 would be y to the 4th. I can divide 12 by 3. Do I need absolute value bars? No. So anytime you have an odd root, you don't need them. So it's odd, odd, even. We don't need it there. And then cube root of z to the 7th. So again, I would take 7 divided by 3. 3 goes into 7 twice, and that's 6. So I have a remainder of 1. So it would be z squared. And then I still have a cube root of z left. And make sure in the radical that you're putting in your answer, you do include that index of 3. That's often forgotten, that index there. So the one in the radical is just like yes. Yes. Yeah. So the exponent on the variable is the remainder. And it should be a number smaller than the index, because that tells you that you can't simplify it anymore. And then that one I don't need to rearrange at all. It's already in the form with the radical at the end, so that would be my answer. All right, so why don't you go ahead and simplify example C, just to make sure you can get one of these without me leading you through it. It is a 4th root, so pay attention to that. All right, looks like we're okay. Be careful, because this is common and I can understand how it would happen, but just be careful for numbers that might be perfect squares and perfect fourths or something like that. Just make sure you're taking the correct root. So 4th root of 16 is 2. All right. The next property then is the quotient property of radicals. And just like for a product where it says if you have a product, you can split it apart, for a quotient or a fraction. Have your attention up here, please. For a fraction, you can split it into the nth root of the numerator over the nth root of the denominator, or vice versa. It is not simplified to have a fraction in a radical. So So if you do have a fraction, that's where splitting it into the radical of the top and the radical of the bottom. And then what we do is, or another thing to remember is it's not simplified to leave a radical in the denominator, so we'll have to rationalize the denominator, which means we're getting the radical out of the denominator. So on the next side, it explains how to do that, but I have examples there to go through. Make sure you understand this phrasing also. So rationalizing the denominator, that means to eliminate radicals from a denominator or fractions from a radicand. So getting a fraction out of a radical or getting a radical out of a denominator is called rationalizing the denominator. And it says to rationalize the denominator, you multiply both the numerator and denominator by a quantity so that the radicand has an exact root. So what this is showing is, in the first row, if the denominator is specifically the square root of something. So this is specifically a square root. Then, in order for the square root to cancel out, I want the b that's here to be a b squared. Excuse me. So what I can do is I can multiply the numerator and denominator by that square root. So if I multiply it by itself, the square root of b, then what I get when I multiply these is I get the square root of b squared, which then the exponent and the radical cancel out, and I just have b. So it gives an example of that if you have 2 over the square root of 3, and you might remember doing this in algebra. You did a little bit of it in geometry with the special right triangles, simplifying those. But if I have 2 over the square root of 3, I would multiply by the square root of 3 on the top and bottom, so that in the denominator, I end up getting the square root of 3 squared, or the square root of 9, which I know is just 3. And then I still have a radical then in the numerator of the fraction, which is okay, but I no longer have one in the denominator. So square roots, I think, are the easiest to work with because you just multiply that square root by itself. But when you have a different root, it's not as simple. So if I have the nth root of, again, b to some power of x. So again, I want the power in the end. I want this power on b to equal the index so that the power and the radical cancel out. So if this n was a 3, I would want this to be b cubed. So then notice it's saying to multiply by the nth root of b to the n minus x. So why that is if I take x and I add to it n minus x, then those x's cancel and it's just n. So what I would get is I would get by multiplying these the nth root of b to the n, which then the power and the radical would cancel out. So what you do is you figure out what would it take to get my exponent to equal the index. What would I have to add to it? And that's what you want your new exponent to be. So it gives an example. If I have 5 over the cube root of 2, and this right now would be 2 to the first power, I want that exponent on the 2 to be a 3 so that the cube root cancels out. So they're multiplying by the cube root of 2 squared, because then the 1 plus the 2 would add to be 3. So this would become the cube root of 2 cubed, which cube root and cube cancel, and now you just have 2 in the denominator. And then you would simplify the top. Okay, so we're going to go through examples of these so you can get an idea of how to work with them. This is where I'm always stressing the practice, the assignments, but especially with these and the simplifying. These are the trickiest when you have these quotients and these fractions. And if you're not practicing that, it's really difficult to get that correct on the assessments because you just don't know what to do. So looking at example 2, we have the square root of a to the 9th over b to the 5th. So what you want to do first, if it isn't already done for you, is split this into the root of the top and then the root of the bottom. So I have the square root of a to the 9th on top, square root of b to the 5th on the bottom. And this won't always be the case. It is with this one, is I notice right now that these exponents are both bigger than my index of 2. So I can simplify both of these first. So if you can, I would say simplify first because it'll just make it easier in the end. So if I simplify the top, divide the 9 by the 2, 2 goes into 9 4 times with a remainder of 1. So that would be a to the 4th power, and I still have a square root of a. And then on the bottom, if I divide the 5 by 2, 2 goes into 5 twice with a remainder of 1. So I would have b squared, and then I'd still have a square root of b. So then the problem is having that square root of b in the denominator. That's the issue. That is what's making this not simplified right now. So what I have to do, again, if you look at the top, when you have a square root, all I have to do is multiply this fraction by that square root, top and bottom. So I'm going to multiply by the square root of b over the square root of b. So on top, I still have a to the 4th. And then the a and the b that are both in square roots, I can write as one square root and multiply those together. So that would be the square root of a times b. And then on the bottom, I still have this b squared. But then this square root of b and this square root of b, that would be the square root of b squared, which I know the square and the square root cancel, that's just b. So then this denominator becomes b squared times this b. And I no longer have a square root. So altogether, I have a to the 4th times the square root of ab all over, and my denominator is b cubed. Okay, and then you do want to make sure, even with the radical that you have in the numerator, make sure that it is simplified. But if you just have variables like this one and both of those exponents are 1s, which are smaller than the index of 2, so I know it's simplified. If you simplify at the beginning, that eliminates simplifying that you'd have to do at the end, usually. But just double check that any radicals you still have in your answer are simplified. Okay, are there questions on that one? Square roots are a little bit easier to work with. So now if we look at b, that's a cube root. So I would have, if I split this, I have the cube root of 2 on the top, and then I have the cube root of 9x on the bottom. All right, and one thing, I am going to show this because it's going to make it easier in the end, but while you're working, if this is confusing to you in any way, then I can show you a different way to think through it. It just requires more simplifying in the end. So look at the denominator specifically. I know 9 is not a perfect cube, so I can't simplify that. So just make sure you're not taking the square root of 9. But I can't take the cube root of 9. And then x, that exponent right now is just a 1, and I can't divide 1 by 3. So right now, there's nothing I can do to simplify like I could do in the previous example. So I'm going to go straight to figuring out what it is I need to multiply by to rationalize the denominator. One thing that can help is I do recognize that 9 is 3 to the 2nd power. So I'm going to rewrite the 9 as 3 squared. So I'm just going to rewrite this and not multiplying by anything yet. So I have the cube root of 2 over, and then I have the cube root of 3 squared, and then I have x to the 1st power. So why it can be helpful to do that is now when I'm figuring out what do I need to multiply by, I have to multiply by the cube root of something. And what I want is the exponent on the 3 and the exponent on the x. I want both of of those to be 3's so that they cancel out with the index. So if I want the exponent on the 3 to also be a 3, I have to multiply the 3 squared by 3 to the first, because then those exponents, the 2 plus 1, will give me a 3. But for the x, it's right now the exponent's a 1. To get this to be a 3, I have to multiply it by x squared. So you're figuring out what exponent do I have to add to that in order to make it equal to the index. And then I have to multiply the top by the exact same thing. So the top gets multiplied by the cube root of 3 to the first and x squared. So again, what's happening here when I multiply these denominators? I get the cube root of 3 cubed and x cubed. So then both of those exponents will cancel the radical out, and my denominator is now just 3x. Then on the top, I'm just multiplying and simplifying. So I have 2 cube roots. I can multiply them together. So I'm going to have the cube root of something. I can multiply this 2 and this 3 to the first that's in there. So that would give me a 6. And then I have an x squared. And that's my answer. So a way to double check, because I rewrote the 9 as 3 squared, that usually helps and means you don't have to simplify at the end. But you could double check. I know 6 is not a perfect cube, and I know the x squared, the 2 is smaller than 3. So I know that this radical is already simplified and that this is my answer. Do make sure that you're not simplifying like this 6 and this 3, because this 6 is in a radical and this 3 is not. So I can't simplify those along with these x's. I can't simplify those. Okay, questions on that one? Okay, so let's look at C together also. When they're not square roots, they tend to be a little more confusing here. So I have a fifth root in this one. So if I break this apart, I have the fifth root of 3, and I have the fifth root of 4y. So going off of how I did example B, if I look at the denominator, is there a way I can rewrite 4? I can write that as 2 squared. Now that won't always be the case. Like if you look at the example right below, that 5 that's there, 5 isn't a number to a power. So you can't always do that, but if you can, that can be helpful. So I would write this as the fifth root of 3 over the fifth root of 2 squared, and then I have y to the first power. So then when I multiply, I have to multiply by the fifth root of something. So I'd multiply by the fifth root of 2 to what power? What power would I want on the 2? Yep, 2 to the third, so that the exponent of 2 and 3 add to 5, and y to what power? The fourth. So that 1 and 4 add to 5. And I have to multiply the top by the same thing. So then I'll again deal with the denominator first. So my denominator, I have the fifth root of, and I would have 2 to the fifth and y to the fifth. So those exponents cancel with the fifth root, and my denominator is just 2y. On top, I can multiply those fifth roots together. So I would have 3 times 2 cubed, and 2 cubed is 8. So 3 times 8 is 24. And then I have y to the fourth power. And you could double check, 24 is not a fifth root. And yeah, because you simplified this, that, like I said, it really is rare then that you have more to simplify at the end, because you had simplified right here by making that 4 and 2 cubed. Any questions on that one? Okay, so I want you to go ahead and do example D. And then you'll have time work on the practice and let me know if you have more questions.